This webcast talks about forces and describes several types of forces. Remember that a force is a push or a pull that is exerted on an object, and a force always requires the interaction of two different objects. There are two broad categories of forces. There are contact forces, which result when two objects actually touch each other. They have contact. Examples of contact forces would be an applied force, or friction, where an object rubs against the second object, or a normal force, where two objects are pressed together. There are several in that category that require physical contact for the force to be exerted. But another broad category of forces are called action at a distance forces. These forces result even when the two interacting objects never have physical contact. They are still able to exert a push or pull despite the fact that they are physically separated. And there are three common examples of this. The one we're probably most used to is gravitational force. The moon orbits our Earth even though the moon and Earth do not touch. And the reason that the moon orbits the Earth is because there is a gravitational force that the Earth is exerting on the moon. Electrical force. Things that have electric charge can either attract or repel each other, and they do not have to touch each other for that force to be exerted. And similarly, magnetic forces also can be exerted even if there's no physical contact. So all three of those are examples of action at a distance type of forces. So now I'm going to go through and kind of quickly mention several common types of forces, and we will explore all of them in more detail later. But for right now, I just want you to be able to understand what is causing these forces and also the appropriate way to label these forces. Okay, so a gravitational force is represented by the symbol F with a G subscript, F sub G. Any two objects that have mass exert an attractive gravitational force on each other, even if they never touch. It's called an attractive force because this force of gravity always tries to pull the two objects closer together. A very common example of this is the gravitational force that the Earth exerts on us and the things around us. We're usually near the Earth, and so we're very common with this force, right? We know that if we jump off of a platform, we fall back down to Earth. If we drop something, it falls to Earth. And the reason for that is because the gravitational force that the Earth exerts on an object points toward the center of the Earth. Near its surface, the Earth's gravitational field has a strength of 9.8 newtons of force on every kilogram of mass. So any two objects in the universe exert this gravitational force on each other, but the force is really only significant when one of the objects is very massive, such as a planet. So, I may be exerting a gravitational force on the lamp over here, but I'm not causing, that force is not very significant. It's not causing the lamp to move. It's not causing me to move. But when one of the objects is very massive, like a planet or a moon, something on an astronomical scale, those forces become large enough to cause things like, for example, if I drop my calculator, it will fall to the ground. The force of gravity is the same thing as the weight force. So force of gravity and weight, they mean the same thing. And if you're near the surface of the Earth, you can calculate that force of gravity by multiplying the mass of the object by 9.8 newtons per kilogram. We should probably talk briefly about the difference between mass and weight. Mass is a property of an object that determines how much that object will resist a change in its velocity. More massive objects require a larger net force in order to accelerate. A very simple example, if I have a bicycle and it's at rest, I can probably push that bicycle and make it start moving. I can make it accelerate from a speed of 0 to some higher speed. But if I wanted to move my car, it's at rest in the parking lot, I probably might not by myself be able to go and push it hard enough, apply a big enough force to make it start accelerating. That's because the car has more mass and it definitely resists a change in its motion more than the bicycle does. The metric unit for measuring mass is the kilogram. That's the standard unit for measuring mass. Weight is different than mass. Weight is the gravitational force that is exerted on an object by the closest planet. Weight is a force. It has both a magnitude and a direction, and the standard unit for weight is the newton. At the Earth's surface, the direction of the force is toward the center of the Earth. So if I want to calculate the gravitational force on a person, I take their mass and multiply it by the acceleration due to gravity, which is represented by a lowercase g. That g is the free fall acceleration. It's 9.8 newtons per kilogram. So here, this man has a mass of 80 kilograms. 80 times 9.8 tells me that his weight is 784 newtons. That is the force of gravity that the Earth is exerting on him, trying to pull him toward the center of the Earth. So mass and weight are not the same thing. Mass is a property that measures an object's change to resistance to a change in its motion. Weight is the force of gravity that a planet is exerting on the object. They are measured in different units. Mass is in kilograms, weight is in newtons, and weight is a vector, mass is a scalar. So they are not the same things. Okay, so F sub g, gravitational force, is the first type of force. Another common type of force is called the normal force. The normal force is a supporting force that occurs whenever two objects are pressed against each other. It is very common that the normal force opposes the gravitational force. So if I'm standing on the floor is supporting my weight. I am pressing down into the floor, and so that's a normal force that I'm exerting on the floor, but also the floor is exerting a normal force on me that supports me and keeps me from falling through. The normal force is always perpendicular to the surfaces that are touching. So the normal force is usually an upward force that is equal in a magnitude but opposite in direction to the gravitational force. So here's an example of a book sitting on a table. The weight of the book is the gravitational force on the book, and that points downward toward the center of the Earth. The normal force that the table is exerting on the book is represented as this F sub n, and it's pointing upward. But normal forces don't have to be opposite of gravity. They can point in any direction. And here's just one example. We've got a person sitting on a chair. So their feet are sitting on the floor. Yes, the normal force on their feet is pointed up. Their sitting on the chair. So the normal force that the seat of the chair is applying to the person is pointing up. But if they're leaning back in the chair, they're pressed into the back of the chair is exerting a normal force that's parallel to the floor. So that is one example of a normal force that is not opposite of the gravitational force. So normal forces can be in any direction. Okay. Another common type of force is a frictional force, which is represented as F with a lowercase f subscript. Anytime two objects slide against each other, there is a frictional force that opposes the motion of those two objects. Friction is always parallel to the two surfaces that are touching and in the opposite direction of the motion. This little figure here shows a man pushing a box, and he's pushing the box to the right. So the force of friction that the floor is exerting on the box points to the left. It is opposing the motion. Another common type of force is the drag force, which is F with the subscript drag. When an object moves through a fluid, such as air or water, the drag force is the force that resists the motion of the object. So here are a couple of examples where drag would be significant. When a car is moving through air, moving through the air around it at high speeds, there is a drag force that is in the opposite direction to the direction that the car is moving. That's because the body of the car is bumping into a lot of air molecules as it moves, and each one of those molecules is exerting just a little bit of force back in the opposite direction. But because the car is going so fast and is large enough, it is hitting a lot of air molecules, and those little drag forces, those tiny forces, add up to a significant amount. Also, an airplane, it's moving in the direction that the engines are pushing it, but there is a significant drag force that is opposing that motion. Another common type of force is the tension force, which is represented as F with a T subscript. The tension force is a force that's transmitted through a string, a rope, a cable, a wire, something that is long and thin, like that. The tension force occurs when two objects are connected by that string or rope or cable or wire, and it's getting pulled tightly in both directions. So in my little example here, I've got a mass or a weight that is suspended from the ceiling by a wire. And so the reason that this mass does not fall down to the ground is because that wire is supporting it and holding it up. So there is a tension force pointing up on this mass that is being supplied by that wire. The tension force is always directed along the length of the wire, and it pulls equally on the objects on the opposite ends of the wire. So, I talked about how the wire is supporting that mass and not letting it fall. But on the other hand, the wire is pulling down on the ceiling. It's exerting a force on the ceiling at the other end of the wire. There's also a buoyancy force. This is less common, thankfully, because we just use the symbol F with buoyancy as a subscript. But the buoyancy force is an upward force that's exerted on a fluid, or by a fluid, that opposes the weight of the floating or immersed object. So if you had a log or something that's, floating in water, for example, as the object is floating, the pressure from the water underneath the object is greater than the pressure from the water above the object, and therefore the difference between them tells us that there's a buoyant force that tends to push upward on that floating object. And then kind of a catch-all term is an applied force. The term applied force is a general term to describe any type of push or pull that doesn't really fall into the categories that we've just described. For example, Jill pushes a box across the floor. So that would be called an applied force. And the symbol for an applied force is F with an A subscript.